Welcome back, everyone. And it's a pleasure to introduce Enrique Becerra from University of Miami, INSA. And he is going to speak about the Peter-Bale property for stacks.
Okay, so thank you. I would like to thank to the organizers for letting me talk in this conference. So I'm going to talk about the Peter-Bale property for stacks. So the plan will be as follows. In the first part of the talk, I just okay. So so this is the plan of the talk. In the first part, I will just introduce some basic notions and motivations for this for the Peter-Bale property for stacks, and then I will state properly what I mean by this, and explore some possible different formulations or reformulations of the Peter-Bale property in this context. And at the end, I will explain briefly what kind of topological obstructions exist against the Peter-Bale property to hold in this wider context of stacks. Okay, so let me just briefly recall what the classical Peter-Bale theorem in the representation theory of compactly grouped states. And basically, it can be thought as a sort of generalization of the classical Fourier analysis, which goes for the circle group. And the Peter-Bale theorem generalized this Fourier type decomposition into the setting of compactly groups. So we can say that this is a sort of non-abelian version of the Fourier decomposition. So suppose that we have this gamma, which is a compactly group in all that follows. And there are various ways to state the Peter-Bale theorem in this context, but let me just recall two of them. The first one is saying that any compactly group is in fact a matrix group. So in other words, any abstract compactly group can be realized as a matrix group as a subgroup, closed subgroup of some unitary group for a big enough dimension. And this turns out to be equivalent to the fact that any unitary representation of a compactly group can be split as a sum of finite dimensional pieces. In this statement here, I choose the regular representation, which is L2 of gamma, which is the Hilbert space, which of L2 functions on gamma. And there is an action by translation of gamma into this Hilbert space, which is, by the way, a separable infinite dimensional Hilbert space. So we have this regular representation, which is unitary and infinite dimensional. And we can split, or one statement of the Peter-Bale theorem, in this case, states that we can decompose such unitary representations into finite dimensional representations. So more specifically, more concretely, we can even just describe how this splitting works in this case. And we can split the regular representation as an orthogonal sum, where this P denotes an irreducible representation of gamma. So we can run over all irreducible representations of gamma. And this lambda P is a certain multiplicity, which is related, in fact, it is equal to the dimension of the corresponding representation. So this is saying that all irreducible representations in the representation theory of a compactly group turns out to be finite dimensional. And moreover, we can decompose the regular representation, or for that matter, any infinite dimensional unitary representation into finite dimensional pieces. So in other words, we can say that for the purposes of representation theory of finite dimensional compactly groups, there are enough finite dimensional representations. Okay, so this is the classical Peter-Bale theorem. And now, The goal of this talk is to investigate a corresponding Peter-Bale type theorem for a generalization of the notion of compact Lie group, which in this case turns out to be the notion of proper Lie groupoids. So proper Lie groupoids are the notion of a proper Lie groupoid is a possible generalization of the classical concept of a compact Lie group. And broadly speaking, very broadly speaking, a Lie groupoid is just a groupoid object inside the category of smooth manifolds. So this means that a Lie groupoid G, that I will denote by G from now on, consists of some data, which in this case, a Lie groupoid consists of a set, of a collection of objects. It's a category object inside smooth manifolds. So we have a collection of objects, and we also have a collection of arrows. But these two collections of objects and arrows are endowed with a suitable C-infinity smooth structure. So moreover, we also have the obvious structure maps that endow this pair of smooth manifolds with the structure of a groupoid. So I write here what are these structure maps. So we have, for instance, for any arrow in G1, we can associate a source and target, which are just objects. So if we have an arrow in G1, so we can think that this arrow is pointing from this source to its targets according to these maps. And we also have the corresponding unitary or identity arrows for any object in G0. And of course, we also have a multiplication, which allows us to compose or to define a composition of any pair of composable arrows. So composable means here that the source equals the target of the next arrow. So in that situation, we can compose arrows according to this map, and we ask that these structure maps are smooth as well. So of course, in order to be able to say that, for instance, the multiplication map is smooth, we need to impose some technical conditions into this structure. For example, we can ask for the source and target maps to be submersions. So in that case, we can define the manifold of composable arrows just by taking the corresponding fiber product like this. And then it makes sense to talk about the smoothness of the composition of arrows. Okay, so this data must satisfy some obvious actions in this case, which ensure that the multiplication is associative, that the identities works just like identities for this multiplication. And we also ask for any arrow to have an inverse. All right, so this is basically what I mean by a Lie groupoid. And Lie groupoids, as I said before, correspond to a sort of generalization of the notion of Lie group, where a Lie group is a group object inside the category of smooth manifolds, and this is a corresponding generalization for groupoids, internal groupoids. So this we can think of this notion of groupoid as a sort of algebraic gadget, but the point or the motivation for us is that Lie groupoids correspond or can be thought also as well as a sort of presentations for a more geometric notion, which is that of a stack, of a differentiable stack. So by this, we can thought of a groupoid as a sort of presentation of an atlas for a more geometric object, which can be thought as a quotient taken in a suitable category, which is the category of stacks. So we can thought of this G as presenting the so-called classifying stack of G. Okay, so moreover, this there is an equivalence, which is essentially due to Mordek and Prompt, which says that in the case of Lie groupoids, in the category, in the C-infinity smooth category, Lie groupoids up to a suitable equivalence, which is called Morita equivalence of groupoids, correspond exactly with these geometric objects, which are differential stacks. So differential stacks can be thought as Lie groupoids up to this notion of Morita equivalence, where Morita equivalence is telling us which is the appropriate smooth version for the equivalence of categories. So Lie groupoids are categories which are enriched with a suitable smooth structure, and we can define, of course, the notion of equivalence of groupoids as plain categories, but we can also ask for this equivalence to have a smooth which respect the smooth structures involved. Okay, so let me just show to you some basic examples of this kind of objects. So for any smooth manifold, if we take any smooth manifold M, then we can define a corresponding stack, which is just the manifold itself. It can be done just as a manifold itself. So in terms of groupoids, we can present such a manifold by a very simple groupoid in which its objects correspond to the points of M, and its arrows are just identity arrows. So this is one possible presentation for a manifold as a Lie groupoid, but we can also define or we can also present a manifold by many other Lie groupoids. For instance, if we take, for example, an atlas of this manifold M, then we can construct out of this manifold a Lie groupoid, which is related with the process of gluing or construct the manifold out of the data which consists of the atlas, the shards, and the way in which these shards are glued together in order to produce this manifold. So in that case, Morita equivalence correspond to the notion of equivalence of atlas in differential geometry, and then we can think of any manifold, any smooth manifold in this way as a stack. Okay. So this is one extreme case. So smooth manifolds, the category of smooth manifolds is embedded into the category of differentiable stacks, but the category of differentiable stacks contains a lot of other objects which are not manifolds. So for instance, if we choose any Lie group gamma, we can produce out of this Lie group the so-called classifying stack of the Lie groupoid gamma. And the point here is that within the category of differential stacks, the stacking maps from any smooth manifold M into this classifying stack of the Lie group gamma corresponds exactly, or can be identified in a natural way with the groupoid of principal gamma bundles over M. All right, so this is the other extreme of this. So we have the whole category of differential stacks, and on the one hand we have all the smooth manifolds, and on the other extreme we have the classifying stacks of Lie groups. So in the middle we have a variety of other types of stacks which combines these two basic notions. So we can think that, or we can phrase this by saying that the category of smooth stacks or differential stacks contains both the category of smooth manifolds and the category of Lie groupoids at the same time. Okay, so of course there are other situations in which these two notions are mixed together in a suitable way. For example, if we take in a smooth manifold M and we endow, or this manifold is endowed with an action of a Lie group gamma, then we can construct, or there is a way to construct out of this data the corresponding quotient stack, which lives in the category, of course, of differential stacks, and is a realization of the, let's say, the correct way or the correct notion of quotient. or so we can take quotients like this inside the category of differentiable stacks, and these quotients remembers everything. So if we take just the quotient topological space of this manifold M, or take just the orbit space and with the quotient topology, then this topological space forgets almost everything about the original action. But by contrast, the quotient stack remembers everything, like the stabilizer groups of the corresponding action and the way in which these stabilizers glue together along the orbit space. Okay, so one way to realize this stack quotient is by means of the action groupoid. So this action groupoid is just a groupoid whose objects correspond to the points of M, and whose arrows correspond to the pairs of points of M and elements of the group which is acting on M. So we just can draw an arrow. So if we take a point M on the manifold M, little m into this capital M, then take any G on gamma. So we can let act this G on M, and there will be an arrow in this groupoid which goes from M into GM. And the composition of arrows is of course related to the product operation in the corresponding Lie group. All right. So now, if Lie groupoids correspond to a general, or is a generalization of the notion of Lie group, then the corresponding generalization, or the corresponding objects which generalize the notion of a compact Lie group, corresponds to this notion of properness. So we will say that a Lie groupoid G is a proper groupoid if this technical condition is satisfied. So this technical condition is saying that the anchor map, the so-called anchor map of the groupoid, which takes an arrow into the pair consisting of its source and target, which are objects on G, is a proper map in the topological sense. So if this happens to be true, if this map is a proper map, then in particular, when we take any object, if we take any object X on G0, then the corresponding automorphism group of the Lie groupoid, which is the collection of those arrows which goes from X and returns to X, which then this automorphism group turns out to be a compact Lie group whenever this map is a proper map. So we can think that for any object X in G0, we have a compact Lie group, and these compact Lie groups varies along the space of objects of our group. So we have a bunch of Lie groups varying smoothly, let's say, along the objects. Okay, so moreover, we also have this consequence of the properness of a Lie groupoid, which says that the set or the collection, which is just the orbit space, the set of isomorphism classes of objects in this G0, and though with the quotient topology, turns out to be a Hausdorff space, and moreover, it is also a locally compact space. So this is just the space of orbits of G0. Okay, so now, for proper Lie groupoids, there is this linearization theorem. It's a kind of local linearization theorem due to Sung and Kreinig. And this theorem says what is the local structure of a Lie groupoid. So if we have any proper Lie groupoid, then locally it looks just like the third example in the previous slide. So in this example, we have a compact Lie group, a Lie group in general acting on a manifold, and we can take the corresponding quotient in the category of differentiable stacks. And the Sung-Kreinig theorem says that any proper differentiable stack or any proper Lie groupoid is locally like this. It's just a quotient of a smooth manifold divided by the action of a compact Lie group, which is, in fact, it can be chosen to be the stabilizer of the corresponding object. So we have a basis for open substacks of a general proper smooth stack, which looks like this. All right. So now let me just explain, or the goal is to this talk is to explain how the Peter-Bale property or the Peter-Bale theorem. We want to understand how far the Peter-Bale type theorem holds for these more general objects, namely proper Lie group points. So, of course, we need to introduce some notion of representations, of linear representations of proper Lie group points, or for Lie group points, by the way, in general. So by a unitary representation of a Lie group point, I just mean a Hilbert bundle, or a bundle of Hilbert spaces defined over the space of objects which are endowed with a suitable unitary action of the arrows. So this means that if a proper Lie group point if we can think of a proper Lie group point as a bunch of Lie groups which are varying smoothly along the space of objects, then a unitary representation of such a thing will correspond to a bunch of unitary representations of the automorphism groups of objects, which varies in a nice way along the space of objects. So this can be formulated precisely or rigorously by saying that a unitary representation will consist of, on the one hand, of a bundle of Hilbert spaces of the space of objects together with a unitary action of arrows. Okay, so from a geometric perspective, if we consider the classifying stack of a Lie group point, then unitary representations defined like this, in this way, correspond geometrically just to the notion of a Hilbert bundle, of a stacky Hilbert bundle over the corresponding quotient stack. So representations are just, let's say, it's a way to present the notion of a Hilbert bundle over a more geometric object like a stack in this way. Okay.
Can you also feel the unitary representation as a Lie group point map from G into some space bound?
Yeah, you can take functors from the group point, which are presenting the stack, into the category of Hilbert spaces. So, but of course, you need to take into account some continuity properties or things like that. So yeah, you can think of a representation just as a functor from G into the category of Hilbert spaces. Yeah. Okay, so well, of course, in particular, if we have or if our stack is just a plane manifold, a smooth manifold, then a representation of any group point which is presenting the manifold, or is just this notion corresponds exactly with the usual notion of a Hilbert bundle over the smooth manifold. And on the other hand, if we take this the classifying stack of any Lie group, then a Hilbert bundle over the classifying stack of such a Lie group corresponds exactly with the notion of a unitary representation of a Lie group. Okay, so these are so we can try to study these representations, this generalized notion of a representation of a Lie group point, and let me. So in order to state properly the Peter-Bale type property, or we need to we need to introduce this notion of a universal Hilbert bundle. So we will say that a Hilbert bundle over the classifying stack of G, or unitary representation of a Lie group point, is universal if it contains any other unitary representation of such a Lie group point. So in other words, we will say that a representation, a unitary representation H of G is universal if any other representation like this can be embedded isometrically and equivariantly into this representation H. So for properly groupoids, it turns out to be the case that there is always such kind of universal representation, which is a theorem essentially due to Fried, Hopkins, and Telemann, which says that any local quotient groupoid, so if we have any topological groupoid which locally looks like the quotient of a space divided by a compact group, then we always have for such kind of groupoids universal representation. So in particular, due to the linearization theorem of Sung and Kreinig, this implies that any proper Lie groupoid has a universal representation. Okay, here are some examples which are related with the previous examples for the two extreme cases of a smooth manifold, compact Lie group, and also the equivariant version of these two basic examples. For instance, if we take any infinite dimensional Hilbert bundle over a C-infinity smooth manifold M, then it is a consequence of Kuiper's theorem, which says that the unitary group of an infinite dimensional Hilbert space is contractible. So this implies that any infinite dimensional Hilbert bundle over M is in fact trivial. So we can identify this H, which is an infinite dimensional Hilbert bundle. I will assume that all the Hilbert bundles which appear in this talk are separable, which means that all the fibers has a numerable orthonormal basis. So in this case, due to Kuiper's theorem, this implies that such an H can be decomposed over M as a product of the standard Hilbert space times our manifold. Okay, so on the other hand, if we take now a compact Lie group gamma, then the universal representation of such a group can be realized in this way. So we can take the regular representation, and we need to stabilize the regular representation. So this stabilization of L2 of gamma contains, in fact, any other unitary representation of gamma. So, in fact, this is equivalent, or this is a consequence, but it's in fact equivalent to the Peter-Bell theorem for compact Lie groups. So if you recall in the first slide, the regular representation can be decomposed in this way, and any irreducible representation appears in this decomposition with certain multiplicity. So compact Lie groups are semi-simple, so we can decompose any representation into irreducible ones. And this implies that if we stabilize the regular representation, then this is in fact a universal representation of gamma. So for smooth manifolds and for compact Lie groups, we have universal representations, so look like this. And locally, if we have a quotient of a smooth manifold divided by the action of a compact Lie group, then we can combine these two previous examples and produce the universal bundle of the stacked quotient. So here, Hilbert bundles over the stacked quotient of M divided by gamma correspond exactly with the notion of a gamma equivariant bundle over M. So we can just take the stabilization of the universal representation of gamma, and this bundle, which is topologically trivial, can be endowed with the diagonal action, and this is an equivariant bundle which is universal for M divided by gamma. So note that in these three examples, in each one of these examples, the universal representation splits, in fact, as a sum of finite dimensional pieces. So, for example, in the first case, we just have a trivial Hilbert bundle over M, and we can decompose this trivial bundle into trivial line bundle. So there is a decomposition into infinitely many trivial line bundles. So in the case of a Lie group, then we can also decompose the universal representation into finite dimensional pieces, which is a consequence of the Peter-Bales theorem, the classical Peter-Bales theorem. And again, combining these two examples, we can prove that the universal representation of a global quotient like this, so this is called a global quotient stack, which is a manifold divided by the action of a compact Lie group. Its universal bundle of such a stack also decomposed into finite dimensional pieces according to the classical Peter-Bales theorem. Okay, so in general, we can state we cannot prove that the universal bundle of a general proper differentiable stack decomposed into finite dimensional pieces, but we can state this as a property of such a stack. So we will say that a Lie groupoid or a stack has the Peter-Bales property whenever its universal representation decomposes or splits as a sum of finite dimensional vector bundles. So finite dimensional representations of G correspond exactly with the notion of finite dimensional vector bundle over the quotient stack of G. And we will say that such a stack or groupoid has a Peter-Bales property if we have a decomposition like this. Okay, so now the natural question is if it is the case that any proper differential stack has a Peter-Bales property or not. And unfortunately, this is not true, and there is a counterexample in this for this kind of stacks, which is due to Enrique's. And this counterexample, in this counterexample, he constructed explicitly proper differentiable stack which does not satisfy the Peter-Bales property. So I will explain a little bit more about this example, but essentially we can construct such a stack by taking the fundamental class of the three-dimensional sphere. So the three-dimensional sphere generates the third homology group with the integer coefficients of S3, which is just cyclic group of infinite cardinality like this. So we have an infinite cyclic group, and we can take the generator, which is given by the fundamental class of S3. So now out of this cohomology class, we can produce an object which is called an S1 GERF over the tree sphere. And this GERF is in fact a differentiable stack. The total space of this GERF, that I will explain later on how to think about these objects, is a proper differentiable stack which does not satisfy the Peter-Bales property. And here an important point is that the class, the cohomology class, which is defining this GERF over the tree sphere, is a non-torsion class. So in the cohomology of S3, which have non-torsion here, and the generator is of course a non-torsion element, and this non-torsionness of alpha is the reason because this stack, which is the total space of a GERF, is not does not satisfy the Peter-Bales property. I will explain this later on at the end. Before explaining these kind of obstructions which appear in this generalization of the Peter-Bales theorem for proper Lie groupoids, let me just explain another or several different reformulations, possible reformulations, which are interesting. The point is that the Peter-Bales property is closely related with several other interesting properties or structural properties of differentiable stacks. So I will explain one by one this in the following slides, but let me just enumerate them. So it turns out that the Peter-Bale property, so we have here, we take a proper differentiable stack X, and the Peter-Bale property is equivalent to these four properties. So the first one is saying that, of course, we have the Peter-Bale property holds if and only if there are enough finite dimensional vector bundles over X, and we can make a precise definition for this property of having enough vector bundles. And moreover, this is also equivalent to the property of X to be a global quotient stack. So as we can see, in fact, the Peter-Bale property is a very restrictive condition of stacks, because proper differentiable stacks will satisfy the Peter-Bale property if and only if it is a global quotient stack. So this is one of the possible reformulations. X is a global quotient stack. The quotient of a smooth manifold divided by the action of a compact Lie group. And we also have these two last properties. So one of them is that the Peter-Bale property is equivalent to a sort is equivalent to this property of being able to embed or stack into an Euclidean stack. I will explain this more carefully later on. So we have this kind of embeddings into these Euclidean models for or these basic Euclidean stacks, if and only if X satisfies the Peter-Bale property. And the last one is a kind of extension of the Pontryagin duality into a non-abelian situation, which is the Tanaka reconstruction theorem for stacks in this case. Okay, so let me explain more carefully each one of these properties. So the first one, which is saying that or a stack has enough vector bundles, can be reformulated in the following manner. So we will say that a stack or this stack X has enough vector bundles if whenever we have an open substack of X, and we together with a finite dimensional vector bundle defined locally on this U, then we can extend E into a global vector bundle defined over all over X. So in other words, maybe we cannot extend strictly the original vector bundle, but we can always find a globally defined vector bundle over X in such a way that the original one can be embedded into this global vector bundle. So this is a precise formulation of the property of having enough vector bundles, and there is a result due to Enrique's, which says that having enough vector bundles is equivalent to these two properties. The first one is just the previous property that I stated in the previous slide, which says that X is a global quotient stack. So a proper differentiable stack turns out to be enough vector bundles if and only if it's a global quotient stack. Or we can also state this property in terms of a so-called effective or faithful representation. So if you recall the original or the classical Peter-Bale theorem at the beginning, then one of the possible formulations of the Peter-Bale theorem is that a compact Lie group can be embedded into a unitary group. So this essentially means that, or it's just the same as saying that gamma has a finite dimensional representation which is faithful. So whenever you have a finite dimensional faithful representation of gamma, this automatically produces an embedding of gamma into a matrix group. So
I thought that perhaps the immunity thesis on your theory related to this embedding was about this embedding a stack model. So how is this related to this enough of
I will explain. I will explain that.
But it can be seen in this manner, like the embedding model is the corresponding analogous to this embedding as a matrix.
Yeah, this is one possible one possibility. So this is so the classical Peter-Bale theorem is saying that any compactly group, any abstract compactly group can be realized as a matrix group, which is kind of an embedding. But that property is in fact related, or it's more its relation is closer to this third property here, which says that there is an effective or a faithful vector bundle. So if we take an effective vector bundle over X, this means that any automorphism group or any stabilizer group for any object can be embedded into the corresponding unitary or the corresponding matrix group of the, which is given by the automorphism group of the fiber of the bundle. So this is perhaps this is one possible extension of that property for Lie groups into the realm of Lie groupoids, and another way to look at this at that kind of realization of an abstract thing into a concrete one, like the embedding that I will explain in the next slide, is that it's more like a witness embedding theorem for stacks.
Yeah, it's just that in this case, this point three, it seems like you're parameterizing by point out the cases that over the classical.
Yeah.
Parameterizing out possible.
Yeah, in a witness embedding, we are parameterizing both at the same time or we are realizing at the same time the stabilizers as matrix groups, and also the transversal part, let's say, of the stack as a submanifold of an Euclidean space. Yeah. Okay, so we have this way to, or we can state this property of having a knock vector bundles rigorously in this way, and this is equivalent to these three properties. Okay, so now, and in fact, this property of having a knock vector bundles is at the core of the equivalence between these five possible reformulations of the Peter-Bale property. So, for instance, it is not so hard to show that having enough vector bundles can also, or it has interesting consequence concerning the K-theory of our stack X. So there is a classical theorem of Siegel which says that whenever you have a global quotient stack, so in an equivariant situation, then having enough vector bundles, equivariant vector bundles, is equivalent to the property of to a certain property of complexes, Fredholm complexes. So a Fredholm complex over a stack in this case, or over a space, or in an equivariant situation, is just a complex of Hilbert bundles over the corresponding space. Such that with some additional properties ensuring that fiber-wise we have complexes of Fredholm operators, let's say. So, which means that the kernel and the co-kernel of the differentials of our complex are finite dimensional. So Siegel proved that whenever we have a stack with enough vector bundles, then this is equivalent, having enough vector bundles is equivalent to say that any Fredholm complex defined over X is chain homotopically equivalent to a bounded complex of finite dimensional vector bundles over X. So in particular, this allows us to define, for instance, the Euler characteristic of a Fredholm complex. So we can take by definition the Euler characteristic as the Euler characteristic in the naive K-theory of X, which is defined in terms of finite dimensional vector bundles over X. So in other words, the naive K-theory, or what I'm calling the naive K-theory of X, is by definition the K0 of the category of vector bundles over X. The Euler characteristic of any Fredholm complex can be defined and takes values in this growth in the group. So this is independent of the choice that we make here of a bounded complex of finite dimensional vector bundles over X. And in fact, this defines an isomorphism of the K-theory defined in terms of Fredholm operators or Fredholm complexes, and the naive K-theory defined just in terms of finite dimensional vector bundles. Okay, so this is one interesting consequence of having enough vector bundles or satisfying the pattern-based property for a stack. And now let me explain a little bit more about this embedding property of stacks. So classically, any smooth manifold M can be always embedded into an Euclidean space. But there is also an equivariant version of this witness embedding theorem due to Wasserman, which says that whenever you have a compact Lie group acting on a smooth manifold, then we can you can find an equivariant embedding of this manifold into an Euclidean space, and though with the action of the orthogonal group. So we have this Wasserman embedding theorem, and just like this last property of having enough vector bundles is equivalent to both properties, the first one to be a global quotient stack and the second one to have enough vector bundles, then the pattern-based property is also equivalent to the ability to embed or stack into one of these Euclidean models, which is just a reformulation of the equivariant witness embedding theorem. Okay. So finally, the last property that I mentioned, which is equivalent to the pattern-based property, is this Tanakian reconstruction theorem. So in the classical Tanaka-Crane duality, we have a compact Lie group, and we ask if we can reconstruct this compact group out of the category of finite dimensional representations of gamma. So if we endow the category of representations of gamma with the tensor product, then we can in fact reconstruct the Lie group in this case, or Lie group in this case. So this can also be thought as a sort of non-abelian version for the Pontryagin duality, which goes for locally compact abelian groups. So if you want to extend or to generalize such Pontryagin duality, this is one possible generalization of Pontryagin duality in a non-abelian situation. So the way in which we can reconstruct our Lie group out of the category representations is just by taking the forgetful functor. So we have the category representations of gamma, and we can we have defined the forgetful functor, which takes a representation onto the just the plain linear space in which gamma is acting. And if we moreover take into account the tensor product in both in the category representations and in the category of vector spaces, then we can produce out of this data a group which is given just as the automorphism group with respect to the tensor product of the forgetful functor, and we can endow moreover this automorphism group with a structure of a Lie group. And there is a canonical duality map which relates these two groups, gamma and the automorphism group of the forgetful functor. And the Tanaka-Crane duality states that this duality map is in fact an isomorphism of groups. So we can reconstruct our group out of the category, the tensor category of representations, but we also need to know what is this forgetful functor. So we need these three pieces of data, which is given by the category representations, the tensor product, and the forgetful functor. And out of these out of these three things, we can reconstruct in this way our group gamma. So there is a corresponding version of Tanaka reconstruction theorem, which is due to Trentinaglia, which says that if you take any proper Lie groupoid, then we can you can take the category of representations, which in this case is just the category of vector bundles of the quotient stack. And since a representation of a Lie groupoid consists of a bundle of vector spaces defined over the space of objects together with the action of the with a suitable action of the arrows, then we can produce a similar forgetful functor, which goes from the category of representations of or Lie groupoid G onto the category of vector bundles over the space of objects of the groupoid. So when out of this forgetful functor, we can just there is a similar construction which allow us to construct a Lie groupoid, which is the Tanaka dual of a Lie groupoid, which is the Tanaka dual of the original Lie groupoid, and there is also a suitable duality map which relate these two groupoids. But the point here is that the Tanaka duality map in the case of groupoids is not always an isomorphism, and in fact it can be shown that the Tanaka duality map for a proper Lie groupoid is an isomorphism of Lie groupoids if and only if the corresponding quotient stack has enough vector bonds again. So far we have stated the Peter-Bell property in this extended context of properly groupoids, and we also have these possible reformulations of such property. Okay, so let me just end this talk by taking a closer look at the obstructions for the Peter-Bell property for general proper differentiable stacks. So in order to state what kind of obstructions exist against the Peter-Bell property to hold, we need to well, I need to introduce some notions. So let me denote by Tn the n torus, the n real torus. So we have the Cartesian product of the circle n times, like this. So this is a compact Lie group, it's an abelian one. And the point is that there exists, or there is an identification between some kind of geometric objects which are called GERFs with the structure group Tn over such an X, and the second cohomology group, check cohomology group of X with coefficients in the sheaf of continuous functions from X onto this Lie group Tn. So a GERF, roughly speaking, very roughly speaking, we can think of a GERF as sort of bundle defined over our original stack. So if you change this second cohomology group by the first one, then there is an identification, or there is a way to realize cohomology classes in the first cohomology group with coefficients in this sheaf by means of principal bundles with a structure group given by Tn. So principal bundles with a certain structure group can be thought as a sort of geometric realizations of the cohomology classes in the first in a cohomology group, in the first cohomology group with coefficients in this sheaf. Okay, so the idea is that if we now take the second cohomology group, then we can think of such a cohomology class, or we can realize such a cohomology class similarly in more geometric terms. But this time we need to glue some local geometric pieces, let's say, according to the torsion given by the second by this cohomology class. And what we get at the end is not just a bundle, a principal bundle over our original stack, but we get something called a GERF over X, which is very much like a bundle, but in this higher categorical situation, let's say. So you can think of a GERF just as a bundle over X, which is endowed with a corresponding projection. And the fiber is just the classifying stack of our torus Tn. So such kind of bundles are classified by cohomology classes here, but moreover, we can also take into account the exponential short exact sequence like this. So we can take the Euclidean, the n-Euclidean space, and here is the exponential map, which goes to the torus, and the kernel is just the lattice of lattice Zn in this case. So using this exponential sequence and the long exact sequence in cohomology, we can identify, or there is a connecting homomorphism, which is in fact an identification in this case, which identifies the check cohomology groups with coefficients in this sheaf, and the third cohomology group of X with coefficients in this free group of finite rank. Okay, so if you take a GERF over X, which is classified by certain cohomology class, then we can push this cohomology class under this connecting homomorphism, and this produces a class on the third cohomology group with essentially with integer coefficients. And we will call this class, the corresponding class, the Dixmier-Doady class of the GERF. So GERFs, since we have here an isomorphism, the connecting map is an isomorphism, this is saying that we can classify GERFs with structure group Tn by means of its Dixmier-Doady class, which is a characteristic class of such a bundle. So bundles or GERFs over X are classified by this characteristic class. It's the Dixmier-Doady class. And now, let me explain how we can use this sort of things in order to state or to investigate the obstructions which appears in the for the Peter-Bayer property. Okay, so in fact, if you recall the counterexample of Enrique's about the presentability of the Peter-Bayer property for stacks, this class here, the fundamental class of the sphere, is a cohomology class in the third cohomology group with coefficients, with integer coefficients, and this produces in fact a GERF according to the previous exposition. This produces a GERF of the sphere, and as I said, the non-torsionness of this class is the reason why this kind of stacks are not satisfying the Peter-Bayer property. So in fact, we can show that this is the only sort or the only kind of topological obstructions which exist against the presentability of stacks or the Peter-Bayer property of stacks. Okay, so now suppose that we start with a proper differential stack like this, and the idea is that we can perform some reduction steps of this differentiable stack in order to detect the topological obstruction. So the first reduction that we can perform of X is the following, which is theorem de Moerdijk. So for any such stack X, we can always produce another stack, which in this case is in fact an orbifold, and this means that the stabilizers groups or the automorphism groups of objects are just finite groups. So we can produce an orbifold like this, which is canonically defined out of this X out of X. And this comes equipped as well with a projection map from X onto an orbifold. So we can produce an orbifold together with a projection like this. And moreover, this projection is in fact a GERF. But unfortunately, this GERF is in general non-abelian. So this means that the structure group of such a GERF is a non-abelian Lie group in general. But in fact, we can do better, and we can construct, or we can reduce this non-abelian GERF into an abelian one by a process or a construction which is reminiscent of the construction of the Bail group of a compact Lie group. So for the case of a Lie group, of a compact Lie group, we can always find a maximal torus inside our Lie group, and in fact the original compact Lie group is can be obtained, or can be obtained as an extension of a finite group, which is the Bail group of the compact Lie group of this compact Lie group, and we can reconstruct our compact Lie group as an extension of a finite group by a maximal torus. So a similar process or a similar construction can be done in this case. And we can start with this Murdyck's projection onto an orbifold, and using some construction similar to that construction of the Bail group of a compact Lie group, we can produce another orbifold, which I will denote like this, and I will call this the Bail orbifold of our original stack. So we can factorize this GERF into two parts like this. So the first arrow here is a projection which goes from our original X onto the Bail orbifold of X. And moreover, the Bail orbifold turns out to be a presentable orbifold in the sense that it is a global quotient stack. So this orbifold is a global quotient stack, which means that it's the quotient stack of an almost free action of a compact Lie group on a smooth manifold. So we have this projection, and moreover, just as in the situation of Lie groups, this projection is a GERF, but this time is an abelian one. And the structure group is a torus, in fact, which is similar to the maximal torus of a compact Lie group. So we have, instead of a maximal torus, we have a sort of maximal GERF living over this Bail orbifold. So we can realize, so this is saying that we can realize any proper differentiable stack as the total space of an abelian GERF with a structure group a torus over a presentable orbifold like this. So this is crucial for the identification of the obstructions for the Peter-Break property, since well, we have this Bail orbifold, and we have the corresponding projection, which is a GERF. But GERFs are classified, of course, but is Dixmier-Loady invariant, and it's Dixmier-Loady class. So we can define the Peter-Bail obstruction class, or the Peter-Bail class of any proper differentiable stack, just as the corresponding class in the third cohomology group of this abelian GERF. So the Peter-Bail class lives in the third cohomology group, but in fact I will take just the non-torsion part of this Dixmier-Loady class. So we can take the class in the quotient of the third cohomology group divided by the torsion part, and this is by definition the Peter-Bail class of X. Okay, so this lives here in this cohomology group, and the idea is that this class, or the point is that this class is measuring exactly whether or not the original stack X is presentable, or it satisfies the Peter-Bail property. And the idea, or well, yeah, so formally or rigorous, or let me just state the theorem. The theorem is saying that a differential stack, which we can assume that it has a compact quotient, is presentable or satisfies the Peter-Bale property if and only if the Peter-Bale obstruction class vanish. So the vanishing of this class is just a way to say that the Peter-Bale obstruction class, or the class which is classifying this GERF, is a torsion element in the third cohomology group. So whenever the Dixnier-Lody class of this GERF is a torsion class, we can show that the total space of the GERF, which is our original stack, satisfies the Peter-Bale property. Okay, so this is the only topological obstruction against the Peter-Bale property. And let me just end by saying a few words about how we can prove such a thing. So the basic idea is that we can use, or we can use the close relation which exists between on the one hand a billion GERFs, and on the other hand projective bundles. So in fact, projective bundles, that is bundles whose fiber is a projective space and whose structure group is the projective linear group, are in some sense projective bundles are just the same as a billion GERFs. So we can construct the Dixnier-Lody invariant of a projective bundle, and out of this invariant we can produce a GERF as well, and this also works in the other direction. We can start with a GERF and take its Dixnier-Lody invariant, and out of this data given by the Dixnier-Lody invariant we can construct a projective bundle. So in a sense, these two notions are equivalent: projective bundles and a billion GERFs. So now there is a classical theorem due to Becerra which says that, for instance, if we have a compact smooth manifold M, and we take a cohomology class in H3, then the corresponding projective bundle which realizes this cohomology class is finite dimensional, or we can choose a finite dimensional realization for this class by means of a projective bundle, if and only if the class is a torsion element in the third cohomology group. That is to say, if we start with a finite dimensional projective bundle, then the Dixnier-Lody invariant of such a bundle is always a torsion element in the cohomology, in the third cohomology, and this also works in the other direction. So if we start with a torsion element, we can construct, or we can produce a realization of such a class by means of a finite dimensional projective bundle. Okay, so the proof of this fact is based on a suitable decomposition of the classifying space of finite dimensional projective bundles. So we can construct a classifying space which classifies the finite dimensional projective bundles over a manifold, and it turns out that this classifying space splits as a product of Eilenberg-MacLane spaces in even dimensions. And out of this splitting, out of this decomposition, we can prove this theorem. Okay. Okay, so well, let me just end by saying that we can generalize this into an equivariant situation, and out of this equivariant version of the third theorem, we can prove this statement, which says that the Peter-Bale property holds if and only if the Peter-Bale class vanish. Okay, so thank you.